All right, this section of the book is going to be about enzymes. So this is a protein that we've talked about. So first off, we're going to start off with a little review. We have metabolism. So if we recall metabolism, this is any chemical reaction that is happening in your cells. Remember, reactants will get converted into products. Sometimes those can be catabolic, where we break things down. Sometimes those can be anabolic, where we build things up. And sometimes they can be what's called amphibolic. We can do both catabolism and anabolism in the same reaction. So, metabolism is any chemical reaction of the body. Now, it turns out that most of the metabolic reactions that you have need a helper molecule. And this is where enzymes come in. So, enzymes, these are proteins that help carry out metabolic reactions. And in the process, this speeds up reactions. Turns out all the metabolic reactions that occur in your body will happen, just not at a pace that's allowing you to stay alive. And the way they speed up reactions is actually by a term called energy of activation. So if we look at figure 5.9, the way an enzyme speeds up a reaction is by lowering the energy of activation. So here is a quick synopsis of the graph. Here is our reaction, and this is the initial energy needed to start a reaction. So in a normal reaction, we would need a certain amount of energy to get that going. The energy from here to here is called the energy of activation. Or you might see this subscripted E sub A. Now, if we bring an enzyme into that same reaction, we're going to have the same starting point and the same ending point, but you notice I only need energy from here to here. This amount of energy and this amount of energy is the difference when an enzyme is involved. So it speeds up reactions by lowering the energy of activation needed to keep it going. So, an enzymatic reaction is going to be very similar to the reactions we've seen before. It's still going to have reactants. It's still going to have products. One of the things, though, that we do change is the name of the reactants. So, substrates. These are reactants in an enzyme equation. So, enzymatic reactions. So we're just giving a fancy name to our substrates, and they still go to products. Because the enzyme is involved in the equation but not used, it's just a facilitator, it will go into the equation as well, but it will go above the arrow, because this is when change is taking place. So the enzyme is involved in changing a substrate into a product, but it itself, while it facilitates, it does not get used. And you can see that they had it in figure, you can see in figure, oh, there it is. You can see in the green box at the bottom of page 88 that they have a series of equations. And chemical reactions are typically not in isolation. So this is a shortened version of what's below. So in this equation, A is the substrate that will get converted to the product B, and it will be facilitated by an enzyme. Then B becomes the substrate in this reaction, and it will become the product C, and that's going to be facilitated by a different enzyme. C will then become the substrate of the reaction, taking C to the product D, and another enzyme will be involved. Another thing that's unique about enzymes is that they often have what is called an induced fit, which means that my enzyme, so this is going to be my enzyme, in green, my substrate will be of such a shape that only it can fit into that enzyme. This site on the enzyme, this is called an active site. It's the active site because that's where the action, the conversion, is taking place. The fact that this substrate fits exactly into that enzyme is called an induced fit. It means there is a one-to-one relationship between the substrate and the active site. And this is how substrates find the right enzyme to go to. For instance, if I had another substrate and it was circular like this, it cannot get into that active site because it doesn't have the right induced fit. So this is our general enzymatic equation. Instead of having the word reactants, we have the word substrates. Substrates will use an enzyme to get converted into a product. This saves the body energy. And then the last thing we need to know about enzymes is that they are a little bit fussy. Now your book has left out a few of these things that I think are very important about enzymes. I'm not sure why our new book has left these out. But enzymes need a certain temperature to work at. So temperature can affect enzyme performance. And the typical relationship, so here we're going to draw a graph. Sorry. On this axis, we'll have temperature, and on this axis, we'll have speed of the enzyme, or the reaction rate. Every enzyme will have an optimal temperature. So if we were to draw a graph, typically the lower the temperature, so let's say this is 0 degrees Celsius, and this is 100 degrees Celsius, an enzyme will typically work very slowly as the temperatures are low, just like you. You don't go very fast when you're cold. And it will grow in a straight line, in a linear relationship. Basically, as temperature increases, the speed of the reaction will increase. It will, however, meet some optimal point. And this would be the optimal temperature. If you go beyond the optimal temperature, you're going to notice that the rate of the reaction drops off like a steep cliff. So when enzymes are cold, they just work slowly. As the temperatures increase, their speed increases until they reach their optimal. At some point past the optimal, though, an enzyme gets too hot and it will denature. And denature means you lose your tertiary structure. Remember, we talked about how proteins have a primary and a secondary and a tertiary structure. That tertiary structure is the functional. So you lose your tertiary structure, you go back to a secondary or a primary structure, which are non-functional. And if they're non-functional, they're not going to work at all. So when temperatures are too cold, enzymes work slowly. But if temperatures get too hot, go beyond the optimal, enzymes will denature. And this is why you will die of a fever. If you get too hot, your enzymes denature. When your enzymes denature, they don't work. If they don't work, you don't carry out metabolic processes. Another thing that can affect how an enzyme works. and that is pH. In pH, we have a little bit of a different relationship. So we're going to draw our same scale. This time we're going to put pH on this line. If you recall, pH on the scale goes from 0 to 14, with 7 in the middle being neutral. We still have speed of enzymes on the y-axis. Every enzyme also has an optimal pH. As an example, enzymes that are in your stomach have an optimal pH of 2. So they don't work really well at 0 and 1. They don't really work well at 3 and 4, but at 2, they are optimal. And on either side of that, if the pH isn't correct, then the tertiary structure isn't going to be correct. On either side of that, it can also denature. So if you're at your optimal, the enzyme will be in its tertiary structure. If it's not at its optimal, it begins to denature on either side. Some enzymes are optimal at acidic conditions. Some enzymes are optimal around neutral conditions. So now, for this enzyme, this is the optimal. So this might be enzyme 1, this might be enzyme 2. Each of them has their own optimality, and when they are not optimal, they begin to denature. Some like to work at, I need to use red, basic conditions. So this would be a third, a different enzyme, and its optimal pH is under basic conditions. Still has an optimal, it will still denature on either side of that. So pH can also affect how enzymes work. If an enzyme denatures, it cannot work. And then the one your book does go into, and I'm not sure why these are left out. Those are very standard in most biology books. They also talk about a third reason why enzymes slow down. And that's called feedback inhibition. So you don't just want an enzyme to just keep making stuff if you don't need it. So if you get a really good system going, you have your substrate, and it creates a product. If you get too much of a product, you don't want to just keep making something just for the sake of making something, because you're going to lose energy, you're going to lose resources. So your body regulates how much of a product is made by feedback inhibition. This enzyme is going to keep doing its job, it's going to keep taking substrates to products. But if you have too much of a product, this product can come back and stop the enzyme. This is why it's called feedback. Your end product is telling you, hey, you got too much of something. Just like you take a survey at the end of your transaction and you give the person feedback so the next time around they can do a better job. Having too much of a product will stop an enzyme. You give it the same kind of feedback you do with a customer survey, and it will stop for a while until there's not enough of that product again. Then it will stop, and then it stopped giving you feedback. No feedback, we keep going forward. If we get too much of that product again, we'll feed back to our enzyme, and we'll stop the production again. Once we deplete our product, we will then have no more feedback to give. The enzyme can start up again. So these are 3 ways that enzymes can be controlled and or affected by different things in the body.